All right, so I already went ahead and worked out the next part of that example. Here's the orthonormal basis that we were going to use from the first example in this section. I'm naming the vectors v1, v2, and v3. And again, remember the formula in the case of an orthonormal basis for representing u as a linear combination of those basis vectors says that these scalars are just the inner product of u with each of those basis vectors. So that's really all it boils down to, is computing those, u with v1, u with v2, and u with v3. Remember, we're using the dot product here, so each one of these is straightforward to compute. I got 10 over root 13, negative 1, negative 15 over root 13, giving me the scalars that I need on my linear combination, or putting this in the form of a coordinate vector, I get this. So again, fairly straightforward, and you can kind of see that we definitely prefer using orthonormal bases to orthogonal bases if given the choice, just because the formulas and the things that we do with them, they just tend to be simpler. Okay, so let's go ahead and move on. Next thing we're going to talk about is orthogonal projections. We have actually talked about this already. In Chapter 3, we introduced orthogonal projections in Rn, and we proved this thing called the projection theorem. So this is the same theorem, it's just in the more general case of an inner product space. That's not necessarily the same as Rn. So just to jog our memories, what is the projection theorem? If you have a finite dimensional subspace W of an inner product space V, then every vector in that inner product space V can be expressed in exactly one way of the form W1 plus W2, where W1 is a vector in the subspace W, and W2 is in the orthogonal complement of W. In this theorem, we use special representations for W1 and W2. W1 we call the orthogonal projection of U onto W, and we represent it this way. That should look familiar. W2 we call the component of U orthogonal to W, and it's got similar notation, just with that perpendicular sign right there. Notice also, if U can be represented as W1 plus W2, we could also solve for W2 and say that W2 is equal to U minus W1, which is the same thing as this, what I'm showing you here. The point of showing you this is because we're going to prove a theorem in a moment that's going to show us how to find this projection here. And then once we have this projection, we can use this difference to find the component of U orthogonal to W. This picture here shows you kind of what's going on in this projection theorem. So this is something we've actually looked at back in Chapter 3, but this is a case of the projection theorem that would apply to R3 in the case where W is a two-dimensional subspace. It's a plane. So if you have some vector u, and notice u is not necessarily contained in W, it's typically not. We would start by finding the projection of u on W. That's the projection of this vector onto that plane. You can see that the projection is a vector that lives in that plane. So this thing is like the W1 in the projection theorem. W2 should be in the orthogonal complement of W. The orthogonal complement is the set of all vectors that are orthogonal to this plane, and we can see that all of those vectors would lie on some line that passes through the plane orthogonally. So there's exactly one vector, W2, that can be added to W1, and you can see that here, such that W2 is on that line, and the sum of those two things gives us U. So that's the projection theorem. But again, this is just in the special case where we're looking at R3. In other cases where we can apply the projection theorem, you can't necessarily visualize it the same way. I'm not proving the projection theorem here because the proof would look identical essentially to what we proved in Chapter 3. The only difference is that all of the dot products in Chapter 3 would be replaced with the more general inner product. But there's nothing really new to go over there. The projection theorem we need for the ultimate goal of this section, which is developing the Gram-Schmidt process. So to help us get there, we're going to start with this theorem. Now this theorem is going to look really, really similar to a theorem that we proved already in the previous video. This one here. But this theorem is not the same thing. So looking at this, if you have an inner product space V and some subspace of that inner product space that we're going to call W, and if you have a basis for the subspace, basis for W, then for any vector u in the larger inner product space, its projection on W can be given in this form. So notice we're not talking about u here. We're talking about the projection of u on W. And this would be a linear combination of the vectors in the basis for W. We know such a linear combination should exist because, again, the projection has to live in W. This is the W1 that we talked about in the projection theorem. But this is not identical to the theorem that we proved previously. It's just very similar in appearance. Part B is the same idea, but with an orthonormal basis. You notice all of the norms would equal 1, and so it simplifies that formula for us. So, in order to prove this, let's let W1 and W2 represent the same vectors that we let them represent in the projection theorem. The two vectors that add up to W, where W1 is in the subspace W, and W2 is in the orthogonal complement of W. Because W1 belongs to W, and because we have a basis, an orthogonal basis specifically for W, we can apply that previous theorem to represent W1 this way. So we are using that previous theorem, but this is not the result we're looking for. Notice the difference between this and what we're trying to prove is that we have W1s here where we actually want U's. So we need to find a way to convert those into U's. Well, we're going to use the assumption here, which is that W2 is part of the assumption anyways. W2 is in the orthogonal complement of W. Notice if I were to try and form an inner product of this form, W1 plus W2 with VI, where VI is any one of these basis vectors up here. I can use my additive property for the inner product to break this into a sum of two inner products, W1 VI plus W2 VI, except because VI is a basis vector for W, that means it belongs to W. And because W2 is in the orthogonal complement of W, it's orthogonal to every vector in the subspace W, including this one. So this has to equal 0 because these two vectors, by assumption, are orthogonal to each other. This just reduces, this goes to 0, which just leaves us with this first inner product. But that first inner product is the same inner product that we're seeing in the numerators of these scalars here, of these coefficients. So that means each one of these inner products can be replaced by one of this form, W1 plus W2 instead of just W1. That's what I do here. So this expression which we have up here replaces the W1s with the W1 plus W2s. The purpose behind doing that is because W1 plus W2 is U. That's where we came up with these in the first place. So now I can change those into U's, and that completes the theorem. And then for part B, like we said, it's just an immediate consequence of part A in using the fact that the norms are equal to 1. Okay? So here's an example I actually worked out already. We're going to use the subspace W of R3 that's spanned by these two vectors. It's very easy to verify that this set is linearly independent because this vector is not a scalar multiple of that one. Remember, you get to do that if the set has only two vectors in it. I'm given another vector U in R3, and it's not too hard to verify that U is not in the span of this. So I'm not saying that U is in the subspace. I'm just saying that U is in R3. But that theorem that we just proved gave us a way of finding the projection of U on the subspace W spanned by these vectors. So what I want is W1 and W2, or the two projections that we need that would add up to U. Okay? So to that end, let's do what the theorem asked us to do. First of all, the theorem specifically works for orthogonal bases or orthonormal bases. And this one happens to be orthonormal. You could verify very easily by taking the dot product of these two vectors. They are orthogonal, and the norm of each one of them is also 1. So this is an orthonormal basis, which is really, really nice to have because the formula is a lot easier. First thing I need is the inner product of u with each one of these basis vectors, u with v1, u with v2. I did that here. Remember, here I didn't state it explicitly, but we're assuming that the inner product is just the dot product. The first inner product comes out to 1. The second one comes out to 3 root 2 over 2. Okay, so that theorem told me that these become the scalars that I multiply to these vectors. So 1 times v1, 3 root 2 over 2 times v2. And those will become the scalars on these vectors to create the linear combination, giving me the projection of u on w, the orthogonal projection of u on w. So I constructed that linear combination here. I didn't write the scalar 1 times v1, but it's there. If you multiply by this scalar and add these vectors together, here's what I get for my projection, for this first projection. Now the component of u orthogonal to w, this other projection, which we think of as w2, we said we would get by just taking what we got here and subtracting it from u. So I'm doing 1, 0, 3, minus 1, 3 halves, 3 halves. I end up with this, 0, negative 3 halves, 3 halves. This and this are the two projections I'm looking for. And if you wanted to verify that these do what they're supposed to do, one, you would want to make sure they're orthogonal to each other, and they are. Two, you would want to make sure that they add up to u, which you can verify that they do. So these are this would be correct then. Okay. Oh, and I put this picture down here. I don't remember what I was going to do with this. I'm going to skip past that. Okay. So here's where we start to get into this thing called the Gram-Schmidt process. This theorem sort of opens the door to that process. And the theorem is stated very simply: every non-zero finite dimensional inner product space has an orthonormal basis. So we've been talking about orthogonal and orthonormal bases for vector spaces, but we have never really stated whether or not we can even assume one exists for a given vector space. We found some for specific inner product spaces, but how are we to know that there's not some other inner product space out there, maybe something we discussed in 6.1, that doesn't even have an orthogonal or orthonormal basis? Well, this theorem says that we never have to worry about that. And this theorem is proven in a really interesting way. It's what we call a proof by construction. Basically, what we're going to do is we're going to say let's consider W as some finite dimensional subspace of an inner product space V. And let's suppose that we have a basis for W. We know that every vector space has a basis. So we can definitely find one. What we're going to do is convert this basis into an orthonormal one. And the process that we do this to prove this theorem is going to create what we call the Gram-Schmidt process. So how then do we do this? Well, what we start with is it's going to be several steps. So step one is to take the very first vector, and we're going to call that V1. When I get done with this, we're going to end up with a new basis, V1 through VR. So I'm converting these U's into a set of V's. But the very first one is just V1 defined to be the same thing as U1. So we keep the first vector. Okay. Now the next thing we're going to do is we're going to take, we're going to define the next V in this sequence of vectors, V2, and we're going to define it to be U2, which we take from the basis up here, and subtract from it the projection of U2 onto W1. And I realize I actually forgot to state what W1 is. So W1, maybe write this right here. W1 is the span of the set containing the vector we just defined, which is V1. And I meant to include that in there. I realize I left that off. I'll go back up here real quick. So I'm going to have to write in these parts, but that's okay. We could do that. 1 second. There we go. Okay, so what we're doing is we're taking the V1 that we just decided was the same thing as U1. The span of the set containing that one vector is a subspace that we call V1. So V2 is U2 minus the projection of U2 onto W1. Now we know from the projection theorem that this is going to produce a vector that's orthogonal to V1, provided it's not equal to 0. But we know that it wouldn't equal 0, because if that were the case, then V2 couldn't be a basis vector. Remember, a basis can't contain the 0 vector. We don't, let me back that up. We don't want V2 to equal 0 because bases can't contain the 0 vector, and V2 is supposed to be in this new basis that we come up with. But if V2 were equal to 0, then that would imply that U2 is equal to this vector right here, which is a scalar multiple of V1. So in other words, V2 would be a scalar multiple of, U2 would be a scalar multiple of V1, which would put U2 in the span of V1, which is equal to U1. So in other words, U2 would have been a scalar multiple of U1, which would mean that this couldn't have been a basis because we wouldn't have linear independence. Sorry, this big roundabout explanation to basically just show that this will not end up being the 0 vector. Okay, so this is a result of our projection theorem. We know that this way of defining V2 will guarantee that it's orthogonal to V1. Okay. Here's visually kind of what's happening here. So if I imagine V1 as just that one vector, and let's think of it as a vector in Rn, then the span of that vector would be a line containing that vector. U2, that second basis vector in the original basis, is projected on to that subspace W1, and then we use that to find the component of U2 orthogonal to this subspace W1. Which is this guy right here. Okay. The next thing we're going to do is basically repeat this process. So now we have two new vectors, V1 and V2. Okay. Together, I can form the span of those two new vectors that we just found. Okay. That creates a new subspace, which we're calling W2. And similar to the previous example, I construct a new vector, V3, defined to be U3, the third vector in the basis that we started with, minus the projection of U3 onto the subspace U2, which, using that theorem that we've already shown, would look like this. The minus is here because I'm distributing this minus into what would have been a sum here. Using previous logic as before, we know that V3 is not going to be the 0 vector, and it follows from the linear independence of our basis. If this were equal to 0, then U3 could be represented as a linear combination of V1 and V2, which are themselves linear combinations of U1 and U2, so we would lose linear independence in that way. Okay, so we keep repeating this process. Every time we get a new V, every time we get a new V in our basis, we move on to the next U in the basis and subtract from that the projection of that U, so U4 and U4 in this case, onto the subspace spanned by all of the V's we found up until this point. And the logic carries through each step. This will never be the 0 vector because that would end up contradicting the linear independence of our original basis. And this new vector, by the construction here, by the use of the projection theorem, will always be orthogonal to all of the other vectors that came before it. The V4 will be orthogonal to V1, V2, and V3, and so on. Once you've done this after a total of R steps, remember, the subspace W is an R-dimensional subspace. Its original basis had R vectors. The set as we established, will be orthogonal because each new vector is being constructed in a way that specifically makes it orthogonal to everything else that came before it. And because it's an orthogonal set, by the first theorem we proved in this section, it's also linearly independent. Because the set has r vectors and W is r-dimensional, linear independence will imply that this is a basis. So we end up with an orthogonal basis. Finally, the theorem that we wanted to prove in the first place actually said that we're looking for an orthonormal basis. But we know that if you have an orthogonal basis, all we need to do is normalize all of these vectors in this orthogonal basis, and we end up with an orthonormal basis. Okay? So that proves the theorem, but more importantly, it establishes a process that we use to convert any basis for a finite dimensional inner product space into an orthogonal basis. And these are the steps again. And for an r-dimensional space, we would need a total of r steps to get each of those v's. So again, here's what we do. To convert the basis, u1 through ur, into an orthogonal basis, v1 through vr, we start by setting the first vector here equal to the first vector here. So that's your freebie. v1 is equal to u1. v2 is going to be equal to u2 minus the inner product of u2 with v1 over the norm of v1 squared times v1. And then that'll give you this second vector. Once you've done that, you use these two vectors in this formula here. You'll have three vectors, three v's. You use all three of those in this formula here, and so on. And that, once you've done that after r steps, the v's can be put into a basis that will be orthogonal. The optional step here at the end is if you want your orthogonal basis to be an orthonormal basis, you can normalize all of the vectors at the very end of all that, and this new basis will be orthonormal. So that's a lot of information in this video, and probably very confusing at this point. We're going to do a couple of examples to sort of close this section out in the next video to hopefully make this more concrete.